In this video, we will learn how to do integration by parts. So this is section 8.2 in our textbook. Our goals are to introduce this new method of doing integration called integration by parts. We will do a bunch of examples where we use this technique. And at the end, we will review all of the methods we've learned for computing antiderivatives. So in this video, we will introduce what integration by parts is. Remember that back in section 5.5, we learned about U substitution. And that was sort of the chain rule, but backwards, a chain rule for antiderivatives. Now we're going to learn about the reverse product rule, a version of product rule for antiderivatives, and that's called integration by parts. So remember that product rule says that if you're doing the derivative of f of x times g of x, you get the first function times the derivative of the second, plus the second function times the derivative of the first. So now I'm going to try to get a formula version of this, but for antiderivatives. So let's first take an integral on both sides. So integral on this side, integral on the other side. When I put my integral, I have to write dx at the end of my function. That's my notational thing. So on the left, we are doing the derivative of this function and then the antiderivative of it, which means those are going to cancel each other, and we're left with just f of x times g of x. Normally, when I take an indefinite integral like this, we need to write a plus c at the end. I'm going to hold off on doing that because we'll have multiple integrals floating around. And at the end, when we derive our formula, we'll see when we work out examples that we will write that plus c, but I'll hold off on the end until we write it. Okay, on the right, let's split this integral up into pieces. So I'll get the integral of f of x times g prime of x dx, and then plus the integral of g of x times f prime of x dx. And now I'm going to rearrange this integral a little bit. So I'm going to write this integral first. So I'm going to write the integral of f of x times g prime of x dx first. And this other integral that I have over here, I'm going to subtract it over from the f of x times g of x. So this will be equal to my f of x times g of x. And now I'm going to subtract from that the other integral of g of x times f prime of x dx. Okay, now at this point, I'm going to introduce some new variables. So I'm going to let u be equal to f of x, just because I see f of x floating around in a bunch of different spots. And similarly, I'm going to let v be equal to g of x, because I also see g of x in multiple spots. Okay, so now, well, kind of like when I do u substitution, let's write what du would be. The derivative would be f prime of x, and of course I got to write that dx next to it. For v, I would write dv equals g prime of x dx. And now if I make this substitution, I'm going to highlight the matching parts. So where do I see f of x? I see it here, and I see it here. Okay. Where do we see g of x? So g of x, I'm calling it v. Well, I see that here and here. And then what about these other parts? So for du, which is f prime of x dx, you know, maybe let me pick a different color. Du is f prime of x dx. I see that here, that's du. And then finally, my dv, g prime of x dx, that is over here. So now if I replace the highlighted parts with these new variables, I get the following formula. The left-hand side becomes integral of f of x was u times g prime of x dx was dv. U dv equals f of x times g of x, well that's u times v, minus the integral, g of x is v, and then the blue part is du. Okay, so I have this formula. This is called my integration by parts formula. And at first glance, we might be wondering, like, what have we done here? We did a bunch of like antiderivatives and moved stuff around and new variables, but what is this doing for us? What it does is it says that if you have an integral that looks like this, we get to rewrite it in this other form. And that's sometimes helpful because sometimes this original integral is quite hard to do. But this other integral that I have over here is easier. So let's do an example to see this in action. So here I have this integral of 4x plus 7 times sine of 2x dx. When I do integration by parts, you want to choose one part of the integral to be the u and another part of the integral to be the dv. For this first example, I will walk us through that, but then as we progress through the section, I'll give more advice on how to choose the parts. So for this example, I'm going to let u be the 4x plus 7. And then whatever you pick for u, dv has to be everything else, including the dx. So everything else is sine of 2x with the dx. And then we have to then find, well, what's du and what's v? Okay, so du, my derivative of u, well, that would be 4, and then I got to write the dx. The antiderivative of sine of 2x. Well, I know the antiderivative of sine is a negative, and I'll leave some space cosine. So I'll have negative cosine 2x. But I got to adjust it because I know that if I do that, if I do the derivative of negative cosine 2x, well, the derivative of negative cosine is positive sine. But then I got to do chain rule. I got to multiply by the derivative of the inside, which is 2. And I don't want that 2 to show up here. So to cancel it out, I have to put a 1/2 in front. So that's my antiderivative of sine of 2x. Okay, so I have all the parts. Now, let's use our integration by parts formula, which says, okay, you'll get u v minus the integral of v du. So u is 4x plus 7. V is negative 1/2 cosine of 2x. So that's uv minus the integral of v du. So v is negative 1/2 cosine 2x. Du is 4dx. So we're really hoping that this new integral is easier than the one we started with. And indeed, like if we simplify it, we'll get plus, and then 1/2 times 4 is 2. 2 cosine 2x dx. So I still get a trig thing, but at least now there's just a constant in front of it, whereas before I had something with a variable in front of it. So this new integral is definitely easier to work out. In fact, let me write that down. This new integral is easier. This is easier to integrate. That's one of the tip-offs that this choice of parts was helpful. Easier to integrate. So let's do that integral and then we'll be done. So this equals, in front, let me just rewrite this. I can move the negative all the way in front, and let's write it as one fraction. 4x plus 7 times cosine of 2x. Let me put that 2 on the denominator. Okay, and then the antiderivative of 2 cosine 2x. So 2 cosine 2x. Well, that's going to be sine of 2x. Right? Because the derivative of sine of 2x, I need chain rule. The derivative of sine is cosine. So I get cosine 2x. But that gets multiplied by the derivative of the inside, which is 2. And that's exactly what I have here. Okay. Remember that I started off with an indefinite integral, so at the very end, I got to put a plus c. And that's it. I got my answer. Okay, so our first integration by parts example, we just worked it out. So in this example, I told us what to let u and dv be. What if we had picked them differently? Like what would have happened? Okay, so what if instead we let u be the sine term, sine of 2x, and we let dv be that 4x plus 7, and there's also a dx there, so that's always part of the dv. Okay, so then what are the other parts going to be? What is du and what's v? I always like to write the u and the v up top, and their derivatives, du and dv, underneath. That's just how I like to line it up. So the derivative sine of 2x, this is chain rule. We just kind of talked about it. You'll get cosine of 2x times the derivative of the inside, which is 2. And then v would be the antiderivative 4x plus 7. So that is 2x squared plus 7x. So if we do our integration by parts, we get, remember the formula is it's uv minus integral of v du. Okay, eventually we're going to use this so often that we'll commit to memory, but it may take us some practice until we get there. So u times v, so that is sine of 2x times 2x squared plus 7x, and then we get minus the integral of v du, so v is 2x squared plus 7x. du is, let me write it as, oh, and I'm realizing I made one small notational error. When I wrote my du, I forgot to write that dx at the end. I always got to write that dx. So let's put that in, dx. So du is 2 cosine 2x dx. I usually like to write the constant in front. Okay, so now if I look at this new integral, this actually looks harder than the one that I started with, because in both of them we have this trig part, but in the one that I started with, it's multiplying like a linear function, a polynomial of degree 1, because I get x to the 1. But now I have a polynomial of higher degree, and that makes it look harder. So this new integral, unfortunately, is harder than the integral we started with. Harder than the integral that we started with. So I'll put a sad face. So this is often a tip-off that we should choose the u and the dv differently. We shouldn't have chosen them in this way. Okay. Backing up one step even further, one of the indicators that we might try integration by parts in a problem like this is, I notice I have a product of things. This thing multiplying this trig part, and integration by parts is product rule, but in reverse. So when you have a product, that's often a tip-off to try integration by parts, but not all the time. Sometimes our previous antiderivative methods will work. I'd encourage you to try like u sub or something for this. It turns out it won't be helpful. Okay, so what are some of the takeaways? Takeaways. Choose the u and the dv in such a way that the new integral, that's this one, so let me write that here, the new integrals, the integral of v du becomes easier. That's the big goal. And we'll get better at choosing the u and dv with practice. So when we're first learning this, it's very natural to pick something for u and dv, and it might end up making it harder. If that happens, don't stress. Try to pick the parts differently. With more practice, we will get better and better at recognizing what to let those be.